When we were dealing with capacitor circuits, we were making this broad assumption that in a capacitor circuit, the flow of charge was the actual flow of charge, the movement of the charged particles, was less important than the long-term results of the capacitors becoming charged due to the movement of those charges through the wires. We ignored the wires, assuming the wires themselves had zero resistance. We never really talked about the flow of charge. It was a means of us understanding how capacitors operate and what their purpose was. Resistor circuits take into account the flow of that charge. And I guess the real way I want to talk about this is eventually we would like to have at least some kind of operational circuits, something that actually does something. But so far, the circuits we've been using don't really have any operation. They can't really do anything. They're a means to help you understand what's happening in an electrical circuit. They themselves are not the circuit you'd want to buy or want to create. At least though with the resistor circuit, we could replace the resistor with something that has function. And if you didn't get this written down yesterday, you might want to get it into your notes now. A bulb is a type of resistor. It utilizes the flow of charged particles to get hot, and under the right conditions, if it gets hot enough, it will give off light. So a simple incandescent bulb, which is what we were using in our laboratory yesterday, is a straightforward resistor. It obeys most all the properties of a resistor. And so although I will almost always use the resistor symbol because it's easier to draw, and we will draw a lot of circuits over the next couple of days, a circuit that has bulbs in it largely obeys the same rules. Now, just to get us back to like 10 days ago, let me remind you a few things about all circuits in which there is a resistor involved. First, like any circuit, in order for it to be a circuit and have the qualities of a circuit, there must be a complete pathway from one side of the battery to the other side of the battery. That is the first thing to understand, is that circuits do not operate unless we set the reference level with the potential and create a point of high potential in the circuit. That's what we're doing by connecting both sides of the battery. The side with the anode is setting the reference level. That's where zero is going to be, relative to the cathode, which is setting the high potential side of the circuit. Yes, the truth is, everything I'm talking about is actually backwards. We know there's no charge going from the positive side to the negative side. It's going from the negative side to the positive side. I have to say that at least now, but I want you to understand that from this point forward, conventional current is the flow of positive charged particles. Now, defined current, right before we left, we use either a lowercase or an uppercase I for the symbol of current. I generally use an uppercase I for static currents and a lowercase I for time-varying currents. That's generally what I do. But in the heat of the moment, when we're just trying to go through one of these circuits quickly, I will probably write lowercase i's because they're faster. But either way, we use a symbol of I for current, and the unit of current is the amp, which is a coulomb per second. I remember asking you politely to take a look at the units involved in this because they're going to come up a bunch. We already know about electric potential. We'll use a capital V for electric potentials, even if they're time-varying potentials. And I won't hardly ever, at this point, write potential difference. I won't write delta V very much. But just a reminder, this is a volt, and a volt is a joule per coulomb. And this brings me to the first thing I want to point out that you may or may not have known yesterday, is that when your circuit is connected correctly and you're drawing current from the battery, then your electric potential is providing energy to the circuit, and your circuit is consuming that energy. That's no better way to see that than right here. If you've been following or you believe in unit analysis, it should be clear that voltage times current will be joules per coulomb times coulombs per second. And if you've had a course in physics, a joule per second should have meaning for you. If you haven't had a course in physics, or you don't remember because you maybe didn't pay as close of attention as you needed to last year, joule per second is the unit for power. And that's in watts. a joule per second. Without proof, I'm telling you that power in a circuit is the product of voltage and current. This is the rate at which energy is consumed by your circuit. Power in a resistor circuit is very similar to energy storage in a capacitor circuit. So with energy storage in a capacitor circuit, we were talking about 1/2 CV squared, or, and I want to remind you, is 1/2 Q times V, the charge times the potential. In the capacitor circuit, our circuits are static. Charge is stored in the capacitor and no actual flow of charge is discussed. In resistor circuits, they're dynamic. So instead of charge being the operative part of a resistor circuit, we'll find that current is the operative part of a resistor circuit. So almost every place where charge was something we solved for in a capacitor circuit, current is going to be what we solve for in a resistor circuit. Oh, I don't want to erase all of that, but oh well. I'll rewrite it. Power equals voltage times current. All right, something else we talked about before we left were resistors. Resistor is an object that attempts to prevent the flow of charged particles. The higher the resistance, the better your object is at preventing the flow of charged particles. So resistance is not a measure of conductance, it's a measure of the opposite of conductance. So a resistor, the actual product, the object that you guys manipulated in lab, attempts to prevent the flow of charged particles. Now, just a couple of reminders. Resistors are simple devices. They have some kind of conducting material in them, but the conductance of the material is relatively low. The resistors you guys used were carbon-filled resistors. So basically, we busted them open, you'd find the same kind of stuff that's in pencil lead. It's more or less pulverized, heated, infused pencil lead. That's what's inside that plastic wrapper. That wrapper's then dipped in plastic and a couple of stripes are put on it. The impurities in that carbon are basically the things that determine how much resistance that carbon has. So they can make them all the same size, physically, but inside of it, the material that's used is slightly different, which is what provides you with maybe 22,000 ohms versus 4,000 ohms. Which brings me to the next thing. Resistor sizes generally are in kilo ohms, mega ohms. A 1 ohm resistor is really small. So although what we'll probably use in class will be simple numbers, actual resistors are not going to be simple. And there's a little more to it that I talked very briefly about, but want to bring up as well. If you'll recall, there are 3 color bands on the resistor, and then there is a metallic band on the resistor. I told you guys when you were rating resistors to line them up so that the color bands were on the left and metallic band was on the right. The color bands tell you the size of the resistance, and there's a color code that goes with that. The metallic band tells you the tolerance of a resistor. Tolerance is a measure of how accurate the resistors are, with how much accuracy they were constructed. Generally, the metallic band is either a bronzish color, a silver color, or a gold color. And gold and bronzish kind of look the same. Most of the time, it doesn't really matter that much because they're all tend to be silver or gold, which gives you either 10% tolerance or 20% tolerance. This isn't going to come up in our coursework, but I want you to understand that when you were taking measurements yesterday, your measurement should have been close, but probably not right on. That's not a mistake of your measurement. It's the fact that the resistors themselves have variance in their size. So although you might grab 10 resistors that all say they're 22,000 ohms, you measure all 10 of them, you're probably going to get a range of values that are plus or minus 10%. Some resistors come with more information printed on them, including how much power they're able to consume without basically bursting into flames. So although a resistor might have on it a value rating, don't assume that it can handle whatever current you want to throw through it. Almost all resistors are, based on their size, determine how much power they can actually consume before the carbon inside will ignite. So little tiny ones can have the same resistance as really big fat ones. But the size of the resistor is less about how much resistance it has and more about how able it is to handle current without coming apart. So unlike capacitors, where their physical size is a clear measure of how much charge they can hold, it's a little different with resistors. Now, don't get me wrong, there will be some size constraints on resistors that we'll describe. Things about their length and cross-sectional area. The material they fill them with has a lot more to do with their actual resistance than they do with capacitors. All right, that was a lot to say very little. So let me bring us back to something I talked about before we left. I connect a resistor up to both sides of a battery. The resistor will draw current from the battery. I'm using the phrasing purposefully. A voltage supply or a battery can have a voltage without actually producing any current. A resistor has resistance without being connected to a circuit, but current doesn't exist until a resistor is connected to both sides of a battery. Current is in the moment, and therefore current is proportional to voltage divided by resistance. This is now how Ohm's Law tends to be written. It's how I would want you to write Ohm's Law. Because although Ohm's Law sounds like it's about resistors, it's actually about current. This is the dependence relationship. Current depends on voltage and resistance, not the other way around. Generally, you see Ohm's Law written like this or like this. There's reasons to write that, sure, but these are not good dependent relationships. Resistance does not depend on voltage and current. Resistance depends on the material that you use to build your resistor. And voltage certainly doesn't depend on current and resistance. So when it comes to the dependent relationship, it is current that depends on the voltage and the resistor that you choose. So that's the dependent relationship. Again, current doesn't exist until you complete a circuit with a resistor and a voltage supply. And it's at that moment that current will be existing. Voltage and resistance exist independent of a circuit. I've said that like 4 different ways. Is that good? Drive the point home? A current doesn't exist until you have a complete circuit. Voltage exists outside of a circuit. A battery has voltage without being used in a circuit. And a resistor has resistance without being used in a circuit. Those are properties of the objects. But current doesn't exist until there's a complete circuit. Jeremy.
So, for a circuit to be a complete circuit, does it need to have a resistor?
There must be a complete pathway for charges to flow from the cathode to the anode for it to be a complete circuit. And although you will disagree with this statement because you might know things, all circuits have resistance in them. So before I hear the question, what about superconductors? It doesn't matter. Superconductor means that maybe the wire that you're using has no resistance, but the power supply does. Batteries have internal resistance. Anything that produces current will have a resistance associated with it. You can't have a circuit without some amount of resistance. It's going to exist somewhere in the circuit. Our circuits are going to be fairly pedestrian, which means we'll assume the wires themselves have very low resistance compared with the objects that they're being used to connect. So yesterday when you guys did the bulb lab, when you're playing with the bulbs, there are wires that were clearly there connecting the bulbs directly to the power supply or the battery. But the wires had very little resistance compared to how much resistance was in the bulb. So they really don't affect the problem. They are unmeasurable compared to how much resistance was in the bulb. This is also the same reason I told you guys when trying to do the lab yesterday and on Friday to choose resistors that are of the same order of magnitude. Some of you grabbed like a 100 ohm resistor and a 22,000 ohm resistor. Well, the problem with that is if you put those two in series, you add 100 to 22,000. that's inside the tolerance of the other resistor. There's no way of knowing if it's even there. And then if you connected it in parallel, you had the reverse problem. In parallel, you probably found that the whole thing was almost 100 ohms. The 22,000 was hardly even there. Well, there's a reason for that. When you deal with things like this, even though, like I said, the wires are going to have resistance, the battery has resistance, they all have a certain amount of resistance in them. We generally find that in our simple circuits, we can ignore the resistance of the wires and focus on the resistance of our components. We will not be able to ignore the resistance in our batteries. And we'll talk about what that is later. That's internal resistance. So we'll get to that here in a couple of bits. We're going to do an internal resistance lab in a minute. But not in a minute, in a couple of days. All right, now that is the stuff from before the break that we covered a little bit, right as we were leading into the break. I want to talk about the new stuff today. Is that okay? So, something that was added to this information from the lab. Resistors, just like capacitors, can be connected in series and in parallel. So, with resistor circuits in series, there is the concept of creating an equivalent resistance that could represent the total resistance of a circuit. So if I have 3 resistors that I connect in series, there is an equivalence, meaning there's a single resistor that I could put in place of those 3 resistors in series. And just to kind of screw with you, it's the opposite of what we had with capacitors. But to be frank, I think it makes sense. If I put more resistors in a row, I'm clearly going to be impeding the flow of current more. So if you place resistors one after the other, well, you're making it harder for electrons to travel through your circuit. That makes sense then that the equivalent resistance would be greater because I'm trying to prevent the flow of charges more and more by adding more of them in a row. Does that make sense? I think that hopefully that's reasonable sense. But what might make less sense is parallel circuits. And this is where I'm going to use a bit of an analogy. Here we have R1, R2, and R3. And of course, there is the idea of an equivalence for that system as well. In the case of a parallel set of resistors, they follow the rules of the inverse. Hopefully by now, you've recognized that this results in less overall resistance. Because we saw this with capacitors when they were in series. When we had capacitors in series and used this function, the overall capacitance was reduced. In this case, the overall resistance is reduced. It's less than the smallest resistor that's in parallel. Why? Why would the resistance be less if they're in parallel? Who's ever heard of the phrase, the path of least resistance? That's why. We're providing more pathways for electrons to travel when I put them in parallel. So if the battery's between these, and I put all these resistors in parallel, all I've really done is provided a whole bunch of new pathways for electrons to move. So although this one might be 100, and this one might be 1,000, and this one might be 2,000, most of the electrons are probably going to go through the one that's 100. And I'll have electrons that will go through the 1,000 and the 2,000, but I bet the total resistance is going to be less than the resistance of the 100 by itself. And think for a minute why that might be true. Current's going to pass through the resistor that's 100 ohms. But there's also going to be a little bit of current going through the 1,000 and a little bit of current going through the 2,000. So the battery sees the possibility of a total resistance that's a little less than 100 because it can push some electrons through that 1,000 and some electrons through that 2,000 as well. Does that make sense? We get the flow of more charged particles than we would get with the 100 alone. Now, if that doesn't make sense, well, mathematically, we're going to have to look at it anyways. So I tend to like to look at the mathematics of it. But keep in mind, the circuit that you see drawn here for parallel, although it looks like they're all forced to be constrained in the wire, remember, The wire offers no resistance to the flow of electrons. The wire is not like a constraining pipe that prevents charges from moving. It's an open pipe, and an unlimited amount of charge can move through the wires. We treat them as if they have no resistance. So it allows any amount of charge to flow through the wires themselves. Now, I didn't prove any of this to you. I have every intention of proving these to you, but not today. I see people have hands up. I don't want to slow down because I'm still doing review of stuff that we've already talked about, but I will answer your question, Jeremy, if it's pertinent and on task.
What's the practicality of putting in
I'm going to make you hold on to that till later. Because practicality, there's no practicality for any of this yet. You have no idea why you would use a resistor or a capacitor in the first place in the circuit. Let's just say that for right now, that's not your job. The practicality of why you would construct a circuit might need to come later. All right? And I'm not trying to be facetious here. I'm saying we probably need to look at an understanding of how circuits work to be able to give you the practicality of it. For the most part, your goal of designing a circuit is because you have a function in mind. Parallel and series do things to the current and the voltage that will be important. We need to see what those things are, and then I think the practicality will come forward. So let's talk a little bit about solving simple circuits. Resistor circuits, in many ways, are exactly the same in their construction and what you have to do to solve them as capacitor circuits, with a couple of minor differences, and I want to talk a little bit about those differences right now. We never talked about the flow of charged particles before. And before I kind of launch into how circuits are solved, we should, at least for a moment, discuss what's actually happening in the circuits, at least to a small extent. Right now I have an open circuit because I have a switch open in the circuit, so no charged particles can move through the circuit. The circuit itself, though, is heavily laden with charged particles. One of the reasons that circuits are almost instantaneous is because when we close this switch, we present an electric field to the entire bit of wire all at once. The moment that switch is closed, every part of the wire experiences an electric field due to the connection to the potential difference. In a short word, this is nearly true inside a wire. We create a potential difference. There's an electric field everywhere inside the wire immediately along the distance of the wire. That's not exactly true. This relationship isn't perfect for a wire, but it's really close. So the moment that switch closes, there's an electric field everywhere. The reason that's important is we are not waiting for charges to leave the battery and make their way to the resistors. If you know anything about chemistry or anything about conductors, is conductors are filled with charged particles already. And unlike insulating materials, the electrons in a wire are free to move through the lattice of the wire. One way to think of that is consider that there are already charges everywhere in the wire in the circuit. Let me just say 2 sentences. The moment the switch is closed, the electric field is everywhere acting on all the charged particles at once. So when we close that switch, all the charges move at once. Every one of them. The charges themselves cannot get too close together or too far apart. They stay the same distance apart all the time. Which means that the moment a single electron leaves the battery, all of them have to shift all at once. There's no room for them to bunch up someplace. Circuits are instantaneous, the switch is closed. So the moment the switch is closed, the current in the circuit moves everywhere, instantly. You don't have to wait. All right.